And let me share my screen so you can see. And let me get to the right display. Okay, so today is Wednesday, February 22nd, and I wanted to begin with, do you have any lingering questions related to analysis of variance? I know at the end of the video from last week, which would have been February 15th, I was able to do one example. And then I provided an additional video that had some further examples. So do you have lingering questions related to analysis of variance since we were unable to meet on Monday? Okay, thank you, ma'am. Since you have no questions, then the plan today is to look at the correlation and regression introduction. I posted a set of fill-in-the-blank notes last night. They're similar to the ones we had for hypothesis testing, because correlation and regression, again, is kind of one of those lockstep procedures. But to kind of give you an update so you know where we are, I've made a few adjustments. We're nearing the end of the course. Technically, the course ends next Wednesday, which would be March 1st. So mindset learning activity number 4 is due by Friday, which is February 24th. By Sunday, which is February 26th, you would have the analysis of variance homework, class participation number 10, and class participation number 11. 10 is over chi-square goodness of fit. 11 is over ANOVA. The Module 4 exam was scheduled to open, I believe, on Friday, but I've bumped that to Monday because I'm not sure that I can complete the entire discussion today. So I've bumped that to Monday. It will open after class Monday at 12:30 and will stay open through Friday, March the 3rd. Again, technically the course ends on Wednesday, March the 1st, but I gave you a couple of extra days. And then the last 2 assignments, the correlation and linear regression homework and class participation 12, will be due by March 1st. Do you have any questions before we get into correlation and regression? Okay, I hope, again, under the announcements last night, I posted the fill-in-the-blank notes. So hopefully you have those perhaps maybe pulled up on your computer or printed out so you can fill them in as we go. So we'll begin the discussion of correlation and regression. This is going to be our first adventure into what is called bivariate data. Okay, up to this point in the course, we have looked at a single variable at a time. Think about it. We looked at age, and we looked just at age. We've looked at eye color, and we looked only at eye color. We could look at GPAs, and we only looked at GPAs. So up to this point, we have focused on one single variable at a time. We can, in statistics, look at more than one at a time should we need and or want to, for analysis purposes. So this is going to be our first adventure into what's called bivariate data. Now, if you know a little bit of kind of about prefixes in English, the prefix bi, like a bicycle, has two wheels. So bivariate means we have two variables that we're going to consider at the same time. Okay, so again, this is our first little adventure. We also, in statistics, we can do what's called multivariate data, meaning maybe we look at 3 or 4 or 5 or 10 or 20 variables at a time. Again, in this 15, well, really, this is an 8-week course. In this short 8-week course, which is just kind of, we hit a lot of different topics, and we skim the surface. We don't really delve real deep into them. We're only going to focus on 2. So correlation and regression is used to determine if a relationship exists between 2 quantitative variables. Okay, remember, quantitative means that we're going to be dealing with numbers. Okay, so we're going to be dealing with numbers. We're going to look at the relationship between 2 numbers. For example, is the volume of sales for a given month related, to the amount of advertising for that month? So we're looking at sales, volume of sales, and the amount spent on advertising. It's 2 quantitative numerical variables. Is a student's score on the first exam related to the number of hours the student studies? So test score, hours studied. 2 quantitative, numerical values. Is the lifespan of an elephant related to its birth weight? Is a person's age related to his or her blood pressure? Okay, so again, we're going to be dealing with bivariate data. So 2 variables are going to be considered at the same time. Both of the variables will be quantitative or numerical. And so correlation and regression is actually 2 procedures that you usually see in conjunction with each other. You don't usually see one without the other. The correlation process determines if a relationship exists between the 2 quantitative, and I'm emphasizing that, variables. And if you look at the word, it really kind of tells you that if you look at the word, cause correlation, again, the prefix co typically means with. So you have correlation, so you have with relation. So the word itself kind of implies that you're looking for that relationship. So ultimately, you have to decide, yes, there is a relationship, or you have to decide, no, there is not. If we decide that there is a relationship, then we move on to the second procedure, which is regression. The regression procedure creates a model or an equation or a formula, whatever word you want to use, of the relationship. If you think back for a minute, in college algebra, oftentimes you may be asked to like write the equation of the line. And so we're assuming that there is a line relationship to be found. And we know how to do that if we do it from an algebra standpoint. We're now going to consider it from a statistical standpoint. And the primary difference is, from a statistical standpoint, we use 5, 6, 10, 20 pairs of numbers as opposed to just 2. In algebra, we often create that model using only 2. In statistics, we can use 5, 10, 20, or so forth. For this course, we are only going to focus on what is called linear regression, meaning we're looking to see, is the relationship linear, or does it look like it's a line? Now, linear is not the only type of relationships that can exist. You can have exponential, you can have logarithmic, you can have quadratic. There are lots of different relationships that can exist. Again, correlation and regression is one of the topics that you can actually take an entire 15-week course on. And in a full 15-week course dedicated just to correlation and regression, you would talk about the linear relationship, the quadratic, the exponential, the logistical relationship. Okay, but again, our limits within this course being 8 weeks, we're only going to focus on the linear. So let's think about, I'm going to kind of give you the steps for the correlation procedure, and then we'll talk about the regression procedure. So typically, if you're looking for, what would the question be? Well, for correlation, the question is going to be, does a relationship exist between variable X and variable Y? Again, go back to the examples that are at the top of the document. Think about it. Is the volume of sales related to the amount of advertising? Is a student's score on the first exam related to the number of hours a student studies? So is there that relationship between variable X and variable Y? So when you begin this process with hypothesis testing, the first step is to identify what's called the independent variable, which we normally represent by an X. Your data is usually presented in a table format, and in a table format, usually the independent variable is in the left column or the top row. Jewel, can you give me just a minute, please, ma'am? something's happening with my daughter, so give me just a minute. I'm sorry for the interruption. Okay, so we identify the independent variable, which is represented by X. And again, usually your data is presented in like a table form. And so the independent is usually in the left column or the top row. Now, it doesn't have to be, but again, that's kind of the standard in the world of statistics. The idea of it being the independent, again, this is one of the few times that statistics and algebra intersect. And the idea of being the independent, this is the variable that you can choose or manipulate. Okay? The independent variable is the one that you can choose or manipulate. Again, think about it in algebra. Oftentimes, and let me go over to a clean sheet of paper for a second. You know, oftentimes in algebra, if you had an equation like y equals x plus 2, and I'm just doing something simple, and you wanted to create a table of values, normally we would select or choose the values for the x. We might choose numbers like, say, -1, 0, and 2. So again, from algebra, that x would be our independent variable. So again, this is one of the few cases where algebra and statistics intersect. So it's important to know which one of the variables that you're dealing with is going to be the independent, or the x, and which one is going to be the dependent variable. And that's the second step, is you have to identify the dependent variable, which is usually represented by the y. And in most cases, it's going to be in the right-hand column or the bottom row. Now, again, it doesn't have to be set up that way. That's the generally accepted format. Another way to kind of help you make a decision is, I have kind of a weird little saying that you can use. It's blank, which would be your y variable, which is the dependent, depends on the x variable, which is the independent. And so sometimes that little saying may help you. Let's go back up here to the examples at the beginning and see if we could identify which of our variables would be the x and which of our variables would be the y. So if I'm thinking about this, would it make sense to say that the volume of sales depends on the amount of advertising or should I say it the other way? Should I say amount of advertising depends on volume of sales? And if you use this statement, oftentimes one of them just really totally doesn't make sense. If you have it in the wrong order, it often does not make sense. And if you think about these two statements, would you like to take a guess? Or would you like me just to go ahead? You think the first one or the second one? The second one, quite honestly, doesn't really make sense if you think about it. How much I spend on advertising is not going to depend on the volume of sales because I'm trying to use the advertising to promote or improve or boost the sales. So this statement really doesn't make sense if I think about it in the context of what is the point of the advertising. So it does make sense to say the volume of sales depends on the amount of advertising. And in that statement, whatever I have first becomes the Y variable, and whatever I have second becomes the X variable. Again, if you think about it in terms of, I'm going to skip down to the last one, okay? If you think about it in terms of a person's age and their blood pressure, okay? Again, think about it. Would it make sense to say that age depends on the blood pressure, or should I say blood pressure depends on age? Well, again, if you think about it, there's no way that I really can't control either thing. I cannot really control a person's age, but nor can I control their blood pressure. It doesn't make sense, at least in my mind, to say that age depends on the BP. I could select a particular person who is of a particular age. So this is the age is the one that I can choose or manipulate. So in this case, again, the first one, the BP in this case would be the Y, depends on the age, which is the X. And it is important that you know from the beginning which variable is the X and which variable is the Y. So that's why that's the first two steps. It's important to know that. All right, then the third step in the process is to review the scatter plot. Now I need to talk about what a scatter plot is, and I will show you how to create one in Minitab. Okay, a scatter plot, let me see if I can get in here and fill in some things. A scatter plot is a graph of those pairs of numbers. Okay, so again, I mentioned they typically are presented in a table form where you have your X in one column and Y in another. But again, they could also be presented as ordered pairs. And so I could graph those ordered pairs where I have a horizontal number line, which we usually refer to as the X, and a vertical number line, which we refer to as a Y. So it's a two-dimensional graph instead of one-dimensional. And again, then at that point, we plot the points that we have, or the data that we have. And there's different type, there's different patterns, but a scatter plot is basically a graph of the pairs of numbers. It's called a scatter plot because the points are scattered on the graph. That's kind of where it gets its name. So we'll learn how to create one, and I'll underline that here. We will learn how to create one in app.minitab.com. Then, once you have it created, you're going to use your eyes, okay? So then at that point, we're going to use our eyeballs and we're going to ask ourselves 3 questions about the scatter plot. The first question we're going to ask ourselves is, does there appear to be an overall pattern within those data points? And that's either going to be a yes or no answer. The second question that I ask is, does the overall pattern appear to be linear? Now, again, we're focusing on linear. So does it appear that the dots could form a line, or that I could draw a line maybe through the middle of those points? And again, that's going to be a yes or no question. The third question then is, does the linear pattern appear to be positive, negative, or 0? And again, that goes back to your algebra days. So you want to think about the slope or the tilt of the line. And I'm going to review that with you. Okay, so if you're thinking about, again, from algebra, and you're thinking about whether or not that linear pattern appears to be positive, negative, or 0, what would it look like? Okay, remember in each case that your X is on the horizontal, the Y is on the vertical. So if you have a positive slope, again, this is a little bit of an algebra review. Positive slope would appear to go up as you move left to right. Okay, it appears to go up as you move left to right. For a negative slope, would appear to go down as you move left to right. And if it's 0, 0 is a flat line. It's flat as you move left to right. It's actually horizontal. Again, that's a carryover from algebra. But we create our scatter plot in Minitab, and then we're going to use our eyes and think about, does there appear to be an overall pattern? Yes or no? Does the pattern appear to be linear? Yes or no? And then, is that linear pattern positive, negative, or zero? Once we've made those decisions, again, remember, we've relied on our eyeballs at that point to make that decision. Okay? We never rely just on our eyeballs. Okay? So then we have to kind of, it's the idea that we're going to verify or confirm. We're going to do it basically algebraically. Okay? Not with our eyeballs, so that I can know beyond a shadow of a doubt that I do have a linear relationship. So again, this is something that we'll do in Minitab. We'll have Minitab calculate it for us. But using Minitab, we calculate the sample linear correlation coefficient. And the symbol for that is an R. Remember, for the sample, we use English letters. For the population, we use Greek letters. You can also have a population linear correlation coefficient. Its symbol is the Greek letter rho. It kind of looks like a P. So let's talk for a minute a little bit about this sample linear correlation coefficient, or we could talk about it from the population perspective. Pearson's product moment. Oh my, it just left me. Correlation, I think it's called correlation coefficient, is the fancy dancy statistical name for what we simply call the correlation coefficient. Okay, it's fancy dancy. It's named after one of the major players in statistics, whose name was Carl Pearson. He's German. And it gives us a numerical measurement of the strength of the linear relationship. Now, a couple of things. One is the Pearson's product moment correlation coefficient only tests or only considers linear relationships. Okay. And it gives us, we use the numbers, the numerical values, to actually calculate this value. So it's a measurement of the strength of the linear relationship. Its value, when it is calculated, will always be between and including -1 to +1, whether you are thinking about it with respect to the sample or to the population. Okay, whether you're thinking about it with the sample or the population. So I want to talk about this idea now for you. Since we have the technology to calculate it, I mean, it's important to know that it's between -1 and +1, but the computer Minitab is going to do the calculations for you. when Miss Ralston was in school and we didn't have the technological advances that we have today, we didn't have the special software. I had a handheld calculator, but it wasn't advanced enough to do these calculations. I would have to sit and do this by hand. And so it was important for me, at least, to know that it was between -1 and +1, because heaven forbid that I get to the end and get something bigger than 1, because then I know I've made a mistake. So again, that just kind of gives you an idea of whether maybe you've entered your data incorrectly or something like that. But let's talk for a minute about what does this mean. Again, we think about this correlation coefficient, again, sort of like a graduated scale. On one extreme, you have -1. On the other, you have +1. And of course, the halfway or the midpoint would be 0. So let's think about what that would mean in this context. If you have a linear correlation coefficient of -1, visually then what you're going to have on your scatter plot is it's going to appear that the data points line up almost in a perfect straight line. This is what we would call a perfect negative linear correlation. Now, it's going to be really, really rare that you have real, live, real world data that lines up in a perfectly straight line. But that's what that means. On the other extreme, where it's +1, you would have, again, your data points would appear to be lined up in a perfect straight line, but they would appear to go up as you move left to right and be positive. So this would be a perfect positive linear correlation. And again, it's going to be very rare that you have real data that line up in a perfectly straight line. If you have a value near 0, or if it's 0, 0 can actually mean one of two things. One possibility is that there's no pattern at all within the dots. Okay, you just have random dots all over. I always think about it like paint splatter. Okay, there's no pattern at all. Or you could have, oops, not that color. You could have a pattern, but the pattern is not linear. So the other option is you have a non-linear pattern. So maybe you have one of those that maybe looks more like a parabola or something like that. So if you have a linear correlation coefficient that's close to 0, that implies you don't have a linear relationship, because either there's no pattern in the dots at all, or the pattern is something other than a line. But again, we think of this as a graduated scale. So, as you thinking about it, that 0 is kind of no pattern at all. If I'm close to 0, then I have a weak pattern. But as I get closer and closer to 0, then my strength becomes strong. Same thing on the negative side. Again, if I'm close to 0, it's a weak relationship. But the closer I get to -1, the stronger it is. Now, the difference is it a positive relationship or negative relationship? So as you move away from 0, where your relationship is weak, the closer you get to 1, the stronger the relationship is. There's not really any set rule for you to decide, okay, when is it weak? When is it strong? Again, it's open to the interpretation of the researcher. The deal is the closer you are to 0, the weaker the relationship, but the closer you are to either +1 or -1, the stronger the relationship. So we calculate, using the data, that correlation coefficient, which is going to give us the measurement of that strength of the linear correlation coefficient. Okay, but then, even then, once we get it calculated, we can't, there are different ways to decide, but again, it's not just a, okay, I think this means that it's strong, or, Susie thinks it makes it weak. We have to have a way, again, to verify that. So that is step 5. In step 5, we want to determine if R is statistically significant, and we're going to use a modified hypothesis test. Okay, we're going to use a modified hypothesis test. So again, we use our eyeballs looking at the graph. We kind of get our gut instinct. We calculate the measurement, and again, we still kind of have our gut instinct thinking about how close it is to 0 or how close it is to positive or -1. But again, we always need to confirm and verify, and that's what we're about to do. And we do that via a hypothesis test. And it's, again, it's slightly modified because we don't necessarily do all of the steps. But we do begin, as we do with any hypothesis test, and we state the hypotheses. You will again have the null hypothesis. Remember, the null hypothesis always contains 0. So the null hypothesis for determining if R is statistically significant will always and forever be that rho, the population linear correlation coefficient, equals 0. Now, if rho equals 0, that means there is not a linear relationship, and R is not statistically significant. And let me give you a big caution here. Guys, this is kind of backwards to what your brain would think. You would think if it's equal to 0, that means there is a relationship and it's statistically significant. No. Okay, again, go back up here to the pictures that I just drew. If we're close to 0, that means I have no pattern or it's not linear. Okay, so be extra careful. Students tend to get these mixed up in the interpretation. Okay, it's important that you realize that if it's equal to 0, that means there is not a relationship and R is not statistically significant. The alternative hypothesis will always and forever be that rho does not equal 0, which means there is a linear relationship and R is statistically significant. In this case, we want rho or R to be something other than 0. So then step 2, we collect our data, identify the information. We'll already have all that. Okay. And so then we want to determine only the p-value. This is the modification. I don't really need the test statistic. Okay, I only need the p-value. No test statistic needed. I mean, if you Minitab's going to give it to you anyways, but you don't need it. All you need is the p-value. And then we're going to compare that p-value to alpha so we can make a decision. We use alpha equals 0.05 pretty much every time. Okay, we use alpha equals 0.05 every time, unless for some reason they tell us to do otherwise. So third step then is to make a decision, and we're either going to reject the null or we're going to fail to reject the null. The same decisions that we made previously by comparing that p-value and the level of significance. The other modification is that ultimately you're trying to decide, is R statistically significant? And ultimately you have to say, yes, it is, or no, it's not. Now, let me backtrack for a minute. Okay, if you reject the null, if you reject the null, that means the alternative is true. So if you reject the null, you're actually going to say, yes, R is statistically significant. If you fail to reject the null, you're going to say, no, R is not statistically significant. That's how you make that decision. If you reject the null, then we say, yes, R is statistically significant. If you fail to reject the null, you will, you will say, no, R is not statistically significant. And then finally, you have to answer really the original question. Typically, the original question was, is there a relationship? So the last step in the correlation process is to conclude if there is a relationship. And again, specifically for us, we're looking at linear between the two variables. And again, we're going to either say yes or no. Now, your conclusion at this point determines what you do next. If you answer yes, there is a relationship, then we continue on to the regression procedure. Because then what I want to do, if I know there's a relationship, then I want to create the model or the equation of that relationship. But if I answer no, no, then I stop. Because that means there's not a relationship. And if there's not a relationship, I can't find a model. But I can still make predictions. I can use the average or the mean of the Y values for prediction purposes. I can still use the average, quote, for prediction purposes if there's not a linear relationship. Jewel, I'm assuming you'll let me know if I'm going too fast or if you have questions. Okay, so let's assume we've gone through the correlation process. we've decided, yes, there is a linear relationship. Okay, so then we want to determine the model, if you want to call it the equation or the formula for that relationship in the form, and you usually see it written y hat equals a plus bx. Now, hopefully, that equation there looks familiar. If you go back to your algebra days, in algebra, we learn about something called the slope intercept form of a line. And normally it's in the form y equals mx plus b, where m is your slope and b is your y-intercept. Well, if you look at this equation or the model that I've written over here, it looks very similar to that. There's a few changes in the notation, okay? Let me write it this way to maybe avoid some confusion. B plus AX. Okay. In statistics, we put a little dunce hat, or sometimes you'll see it written Y with a little tick mark beside it. And that basically lets people know that this was a regression or a statistical model, as opposed to one that you create in algebra. Because typically in algebra, we only use 2 points. Well, statistically, I can use 2 points, 5 points, 10 points, 20 points. The more points I have, the better the model. And so that little dunce hat or the tick mark next to the Y lets someone know that this was a statistically created model where more than 2 points were used. The B is still the y-intercept of the graph. They use the letter A instead of M because it represents the average rate of change, which again is the concept of slope. But for average rate of change, again, I've considered more than 2 points. I may have used 3 points or 5 points or 10 points. So it's the same idea. But again, we're utilizing maybe 5, 10, 15, or 20 ordered pairs as opposed to just 2 like we do in algebra. Now, Minitab is going to determine that model for you, and it doesn't say that here, so let me make a note. Okay, we will do this in Minitab. Once I have the model, I want to use the regression model to make a prediction given a value for, usually you get the X or the independent variable. And I'm not sure what I got this and part down here for. Okay, so once you have the model, we can then use the model to make a prediction. Usually you're given the value for X, which is your independent. And then it's kind of weird, the way that it's kind of set up in this text. At the end of the process, you actually go back and decide, is it even appropriate to use, say, age to predict blood pressure? Okay. Is it appropriate to use the birth weight of an elephant to determine his lifespan? Is it appropriate to use the amount of advertising to determine the volume of sales? And again, it's at the end. We could have done it at the beginning, okay, but for some reason they have it at the end. So the last steps here are to decide if the independent variable is a good predictor for the dependent variable by determining what's called the coefficient of determination. The coefficient of determination is the square of the correlation coefficient. It is R squared. And we answer yes or no. Now, this is one case where Miss Ralston is going to kind of let you wave your hand at her. Okay, we're not going to try to do an additional test or anything like that. We're going to use a rule of thumb. Okay, if R squared is greater than 50%, we're going to say, yes, it's a good predictor. Now, as a side note, your R squared value will always be, let me move this over. Your R squared value will be between 0% and 100%. Remember that the limitations of R were -1 to 1. Well, if I square those, -1 squared is 1. +1 squared is 1, so that's where I get the 100%. So I'm never going to get a negative value, okay? Because if I square a negative, I'm going to get a positive. And so the lowest it could be is 0. Again, also think about this like a probability, 0 to 100. The coefficient of determination is usually stated or written as a percentage. And then the last step is to interpret that coefficient of determination. What does it tell you? And I have the exact sentence that you'll write. Now you have to fill in the blanks, but the interpretation of the coefficient of determination should be written this way every time, all the time. It is approximately R squared percent of the variation. I'm writing it in red and capital letters because it's important. In the Y variable is determined by the variation in the X variable. kind of gives us an idea of as the y changes and how much, the change in the y or the change in the x, how does it affect the change in the y? Okay, you have to put those words variation in there. It's always approximately r squared percent of the variation in the y is determined by the variation in the x. You have to put those words in there. Okay. I do need to finish a little early today, so I need to finish about 11:30. So we've got about 45 minutes left, and I'd like to try to work through at least one example so that you can see how all this works in Minitab. Okay, so the first example, which is at the end of the fill in the blank notes, says the following are advertised sale prices of color televisions at an electronics store, and it gives you the table of values. Is there a connection or is there a relationship between the size in inches of the color televisions and the advertised sale price? Okay, and so then these questions that I have listed here are the exact questions that you will see on the homeworks and on the test. Okay, I think I have everything updated. I know it's that way on the test. Okay, so the first thing we have to do is to decide which one of the variables is the x and which one is the y. So if I go by the standard rule that I mentioned to you earlier, the top row typically is the x and the bottom row is the y. So let's see if that makes sense. That would mean that the sale price, which is the y, depends on the size, which is the x. That makes sense to me. If I think about turning it around, we would say that the size depends on the sale price. Well, that doesn't make any sense. Okay, so again, if I follow kind of the standard setup here, then my independent is the size of the TV in inches, which is the top row of the table, and my dependent is the sale price, which is in dollars. Okay, then we need to create our scatter plot. So let me kind of give you some pointers or some information about doing the scatter plot. Okay, obviously the first thing we're going to have to do is enter the data. I would put in column 1, I'm going to put the X, which is the size of the TV. And in column 2, I'm going to put the Y, which is the sale price. Okay, you want to keep them paired together as they're given. And let me see if I think I already have my data written down. Let me see real quick. Maybe not. Yeah, I do. Okay, so I already have my data. I've already printed it off. Okay, so I'm going to go over to Minitab. is thinking about it. Okay, you can't do anything in Minitab without the data. So in column 1, I'm going to put the size of the TV. It's in inches, and I'm going to label that as my X. I like to label the fact that it's X at the beginning because that's going to help me later. Okay, so I like to indicate which one is the X and which one is the Y. And then in the second column, I'm going to put the sale price, which is in dollars, and that's my Y. Okay, so I have 9, 20, 27, 31, 35, 40, and 60. And then I have the sale prices. 187, 297, 447, 1177, 77. Okay, so I've entered the data. Okay, then let me go back and I'll write down the keystrokes for you. Once you have your data entered, we are ready to create the graph. So we would go graph, and we're going to choose scatter plot. And then I need to look because I don't remember. Graph, scatter plot, one variable Y, simple. One Y variable, simple. And then you have to choose your Y variable and choose your X variable. That's why I like to label the X and the Y, because I already have them labeled. I don't have to go back and keep identifying or guessing which one is the X and which one is the Y. Okay, so then we're going to select Y variable, select X variable, and then we're going to click OK. Okay, so you got to enter your data first, and then we go graph, scatter plot, one Y variable, simple. We select the Y, we select the X, and click OK. And I'm going to walk through that again. Okay, so I've entered the data, graph, scatter plot, one Y variable, keep it simple. My Y is in column 2, my X is in column 1, and I click OK. And it gives me this scatter plot. I'm going to copy the graph over to my paper. Okay, so we get this picture. Looking at this picture with my eyeballs, I have to ask myself 3 questions. Does there appear to be a pattern within the dots? Well, yeah, I can kind of see a pattern, so I'm going to say yes. Does the overall pattern appear to be linear? Meaning, could you imagine drawing a line through some of the points? Now, to me, it doesn't look real strong linear, but yeah, maybe. So I'm going to say yes. And I do notice that as the size goes up, the price goes up, which means it's positive, which hopefully you can kind of see that by the little dotted line that I drew in. Okay, so visually, I feel like there is a pattern. I'm kind of iffy on if it's linear, but it does appear to be positive. Okay, so then I need to calculate the linear correlation coefficient. And let me double check myself on how to do that. Okay, so to calculate the linear correlation coefficient in Minitab, we go to Stat, Basic Statistics, Correlation. And let's see. So we go Stat, Basic Statistics, Correlation. We choose the variables. We choose the X and the Y. Okay, so then we're going to choose X variable and the Y variable. Then I'm going to click OK. Now, I've already entered the data. So once the data is there, it's there. I don't have to keep re-entering it. Okay, so again, I've looked at the picture. I feel like there is a pattern. I'm iffy on whether it's linear, and I do believe it's positive. As the price goes up, or excuse me, as the size goes up, the price goes up. So then I want to calculate the linear correlation coefficient. So we go Stat, Basic Statistics, Correlation. I want to relate the size of the TV and the sale price. The order that you select them really doesn't matter. And then I click OK. Now this gives you the graph again. Okay, gives you the graph again. If you'll scroll down, it gives you the correlation. Okay, wrong page, sorry. Okay. Let me get where I can paste it. Come on, baby. Okay, so once we do base stat, we find the header correlations, and this number right here is R. So R is 0.894. Now, if I think for a minute with my gut, one is I notice this is positive. And remember we had said that visually it appeared to have a positive pattern. So that seems to fit. 0.894 is reasonably close to +1. Remember when we said the closer we were to 1, the stronger the relationship. So my gut is telling me that based on this number, there does appear to be a linear relationship. But again, I don't get to rely just on my gut. I then have to prove and verify that that is statistically significant, that there really is truly without a doubt a linear correlation. So I'm going to conduct a hypothesis test. And I'm going to say that rho equals 0 is my null hypothesis. But remember what that means. If rho equals 0, there is not a linear correlation and R is not statistically significant. My null hypothesis is always rho equals 0. The alternative is always rho does not equal 0, which means there is a linear correlation and R is statistically significant. So then I need to conduct my hypothesis test. Okay. And I use Minitab to do that. So let me give you the Minitab strokes there. I need to remind myself. And make sure this is the right command. Yep. Okay. So we go to stat. Don't do that. Stat, regression, regression, fit, regression, model. Then you have to select the response variable. The response variable is always and forever the y variable. Then you have to select the continuous predictor. The continuous predictor is always and forever the x variable. And then we click OK. Now, I will tell you, when you do this command, when you use this command, you get everything needed to finish the problem. Okay, this one command gives you all of the information under different headers that you need to finish the problem. Okay, so that's a very important command. Okay. All right, so we're going to do this. We're going to go stat, regression, regression, fit regression model. Okay, I choose my response variable, which is the y. I choose my continuous predictor, which is the x. And then I click OK. To find the p-value that I need for my hypothesis test, I find the header labeled analysis of variance. Okay, I find the header analysis of variance. And I'm going to look for the p-value. It's right here. Notice it's the same on both lines. So my p-value is 0.007. Okay, so I do the command and I look for the header analysis of variance. And then on the table, I look for the p-value. Then I'm going to make a decision. I make a decision by comparing the p-value that I have from Minitab. We're going to compare the p-value to the level of significance, which we always use 0.05. So I have 0.007, that's my p-value. We compare that digit for digit. So first number is a 0, second number, I have a 0 compared to 5. 0 is less than 5, so the p-value is less than or equal to alpha. When p is less than or equal to alpha, we reject the null. Now remember, if we reject the null, that means the null is false or wrong, and the alternative is true or correct. So then it asks me, is the linear correlation coefficient R statistically significant? Well, we've said that the null is false, the alternative is true. If the alternative is true, that means there is a linear correlation and R is statistically significant. So the fact that I rejected the null means that the R is statistically significant. And there is a linear correlation between the size of the TV and the advertised sale price. Listen carefully. If you reject the null, you must say, yes, it is statistically significant. You must say, yes, there is a linear correlation. Guys, the answer to 5D and number 6 should always match. This answer and this answer should always match. So we've decided that there is a linear relationship between the sale price and the size of the TV. So then we get to question 7, and we want to find the model for that. Now again, those commands that we just did a while ago, stat, regression, fit regression model, have already given me that answer. I just need to look for it under the blue header, regression equation. Okay, under the blue header, regression equation. Oops, see if I can get it in the right place. Okay, so here is the way it's written in the computer. Guys, you need to write it in the proper format. And we don't use the words when we write it out in symbols. We would have y hat equals negative 749 plus 54.8 times x. So you can see the y and the x, get rid of the words. There's your model. Question 8 then says to predict the advertised sale price of a 55-inch color television. Okay, so they tell you you want to purchase a 55-inch television. The size of the television was the X. So they've given you the X value. You are going to plug and chug into the model. So I'm going to substitute that value into the model. So I would have y hat equals negative 749 plus 54.8 times 55. Okay, and I'm going to get my calculator out. I have negative 749 plus 54.8 times 55, which gives me 2,265. So the predicted cost of a 55-inch television is $2,265. Then we're on to question 9. Question 9 says using the coefficient of determination. Again, we get that coefficient of determination is going to come from Minitab. And I've already found it. I just have to look for it in my results. This one, we scroll to the header, Model Summary. Okay, now you have to be careful because if you look here, you have R-SQ, R-SQ ADJ, and R-SQ PRED. Okay, you want R-SQ. SQ stands for squared, so that's R squared. That's the one you want. So R squared is 80%. Miss Ralston told you to use the rule of thumb that if R squared was greater than 50%, then we say yes, it's a good predictor. Well, I hope you realize that 80% is greater than 50%. So we can say yes, the size of a color TV is a good predictor of the advertised sale price. And then I have to ultimately write the explanation for the coefficient of determination. Okay. I gave you the wording. We would say, oh my goodness, approximately 80% of the variation in the sale price in dollars can be determined by the variation in the size of a color TV in inches. Okay, again, I used the phrasing that I had above, and I've filled in the blanks. I had to fill in R squared. I had to fill in the Y variable, and I had to fill in the X variable. The other piece that is extremely, extremely important is you have to include the word variation. Okay, that's one problem start to finish. I want to see if I can get through the second one. I maybe won't have to do as much explanation because I've already given you the keystrokes for Minitab. Okay, so let's see if we can walk through a second one before we leave for today. Okay, it says we're interested in exploring the relationship between the weight of a vehicle and its fuel efficiency. The data in the table show the weights in pounds and the fuel efficiency measured in miles per gallon for a sample of 12 vehicles. So again, I begin by identifying my X and Y. Again, if I use the standard setup, I'm going to assume that the weight is X and the fuel efficiency is Y. If I think about my little saying, that we're saying that fuel efficiency depends on weight, which quite honestly makes sense to me. If I think about turning it around, weight depends on fuel efficiency. That doesn't make any sense. So based on the setup, the independent is the weight, which is in pounds, and the Y is the fuel efficiency, which is in miles per gallon. Then I need to enter the data into Minitab so that I can create the scatter plot. So I'm going to get a new worksheet. And in column 1, I'm going to put the weight, which is in pounds, and that's my X. In column 2, I'm going to put the fuel efficiency, which is in miles per gallon, and that's my Y. Again, I like, and it's helpful to label the X and the Y from the beginning. Okay, so I enter the data. Again, I already had it printed out. You want to be very careful. Make sure that you type the data in correctly. You also want to keep them paired. Oops. Correctly. I'm having trouble typing. Okay, I tend to type all of the X's first, and then I go back and put in the Y's. You can do it however you choose. Okay, so I've entered the data. Now I'm going to create my scatter plot. So I go graph, scatter plot, keep it simple. My Y is fuel efficiency. The X is the weight. I click OK. And I get my scatter plot. And I'm going to take it over to my paper. So looking at this scatter plot, again, I'm going to ask myself, does there appear to be a pattern? I think so. Does it appear linear? Yeah, I think so. And this one appears to be negative because the data appears to go down. As the weight goes up, fuel efficiency goes down. So I'm going to say, yes, I believe there is a pattern. Yes, it appears linear, and it is negative. So that's what my eyeballs are telling me. Okay, but remember, we don't rely just on our eyeballs. We have to verify. So I'm going to calculate the correlation coefficient in Minitab. I've already entered the data. It is stat, basic statistics, correlation. Choose the two variables that you want to correlate, X and Y. Click OK. Again, I get another scatter plot. I scroll down to correlations. And I get this number right here. Now be careful and don't miss the negative sign. So this is negative 0.728. Notice again visually we had said it was negative, so the actual R value is negative. 0.728. I'm not super close to 1 or -1, but I'm reasonably close. Okay, so I'm reasonably close to -1. But I don't get to rely on my gut. Okay, I have to test the hypothesis. The null hypothesis is that rho equals 0. The alternative is that rho does not equal 0. And then I have to find my p-value and all that kind of stuff. Remember, this last set of commands gives you everything that you need. So I have stat, regression, regression, fit regression model. The response is always and forever the Y. The continuous predictor is always and forever the weight. I click OK. And again, I need to look for initially the ANOVA. The ANOVA, again, gives me the p-value. Now, it is just pure circumstance that the p-value for this problem is the same as it was for the first example. Okay, it is not always going to be 0.007. Okay, it just happens that the two examples Miss Ralston selected turns out to be that value. Okay. Then I compare my p-value to alpha. So the p-value, which again I get from Minitab, is 0.007. My alpha is 0.05. Again, if I compare that digit for digit, first number after the decimal is 0 for both values. Then I have 0 compared to 5. 0 is less than 5, So the p-value is less than or equal to alpha. When p is less than or equal to alpha, I reject the null. If I reject the null in this scenario, that means that R is statistically significant and there is a linear correlation between the weight in pounds of the vehicle and the fuel efficiency. I then need to find the model, which I've technically already done with that last set of mini-tab commands. I need to find it in the results. In the top half of my screen, I find the regression equation. Again, I need to write the regression equation. I need to write it out without the words. So I have y hat equals 45.44 minus 0.000640x. Okay, it is an equation or a formula. You must have the variables in there. You have to include the x and the y, not just the numbers. Then, now that I have the model, I can make a prediction. And the value that they give me for making a prediction in this problem is 3,500. It says vehicle weighs 3,500. Again, this is the weight, which was the X that, as we indicated in the original setup. It is a plug and chug. Don't overthink it. I have y hat equals 45.44 minus 0.00640 times the 3,500 pounds. Again, I get my calculator. 45.44 minus 0.00640 times 3,500 equals, whoops, that's not dollars, sorry, equals 23.04 miles per gallon. So roughly a vehicle that weighs 3,500 pounds would have about a 23 mile per gallon fuel efficiency. Then I need R squared. R squared is under the header model summary. Again, you get 3 different values for R squared. Make sure you read the appropriate one. It is plain old everyday R squared. And in this case, it is 53.06%, which is slightly above the 50% rule of thumb. So we would say, yes, weight is a good predictor of the fuel efficiency. And then I have to write an explanation. Okay, so my final explanation, I would say approximately 53.06% of the variation in the fuel efficiency can be determined by the variation in the weight of a vehicle in pounds. And there you go. Okay, again, let me remind you of what's due. Mindset learning activity number 4 is due by Friday, which is February 24th. By Sunday, February 26th, you need to complete the ANOVA of analysis of variance homework, class participation 10, class participation 11. By Wednesday, March 1st, you need to do correlation and linear regression and class participation 12. The Module 4 exam will open on Monday, which is February 27th at 12:30 p.m. and will close on Friday, March the 3rd. You have all of the information. You can complete all of that work with the exception of the test till it opens. We will have class on Monday, February the 27th, and I'll clear up any issues you have related to Module 4 in preparation for that exam.